Hello, everyone. Welcome back. Time for the next session. And our first speaker for this session, who also is the theme of the session, I guess, is Axel Ljungström, who will tell us now some properties of Whitehead products. Take it away.
Right. You can hear me, right?
Yes. Yes.
Yes. Okay. Thank you. Right. So yeah, I'm sorry I can't be in Italy with you. I'm reporting it from Stockholm, Sweden instead. But it's not too bad here either, I guess. We have good food here too. Um, I'll be talking about Whitehead products. So what are these? These are from a multiplication on homotopy groups. It takes you from the nth homotopy group and lands you in the n plus m minus 1th homotopy group. And these are useful for a bunch of things, but for example, for constructing non-trivial elements of homotopy groups. So one example is this Bruni number guy is one example of one of these Whitehead products, but there are obviously uncountably many other examples you can give. So classically, these guys satisfy a bunch of nice properties that I'll return to, so you don't have to read this super carefully now, but they are bilinear. They satisfy this graded symmetry. So F multiplied with G is the same as G multiplied with F up to this annoying sign. And you have this Jacobi identity, which is basically your usual Jacobi identity, but up to a bunch of signs again. Okay, so this talk is about Whitehead products and in particular these properties. So first, let me just, now it's not, oh, this because I did that. Clever. Okay, now. So let me first just give you a brief history of the Whitehead products and their status in hot. So I think the first mention of Whitehead products in hot was probably in Brunner's thesis, where he used them to construct the Brunner number. He never really proved anything about them. He just used them out of the box. And then it was kind of quiet for a while, and Ali Shaglayan wrote this nice post about them on the hot mailing list. But then it got quiet again until 2023, where this is paper on central H spaces and bounded types by Ulrich Buchholz and company, where they relate, among other things, among other things, the vanishing of certain Whitehead products to H spaces on certain H space structures on certain types. And a year later, there's this paper on symmetries of spheres in univalent foundations, where they construct by Khan and friends, where they construct EHP sequence and they compute this homotopy group, and they do so assuming bilinearity of Whitehead products. So this is the first time I've been able to find in the literature where someone in hot has actually been crucially relying on bilinearity. And then in 2025, actually in the future, Tom Jack and I will tell you about the computation of pi 5 of S3, which also relies on Whitehead products and in particular on their bilinearity. Okay, so conclusion, Whitehead products seem important enough in hot, but we still don't know much about them. And I was particularly interested in proving bilinearity, since at least two independent projects seem to use them. Use this property. But it was sort of a lucky coincidence that the proof technique I came up with actually works just as well for the other properties. So yeah, I'll tell you about this proof technique today. We will need some very light background, which I edited 2 minutes before I started. So let's hope it's still correct. Smash products and suspensions. So first of all, smash products, what are they? Well, I'll just remind you quickly that you can take a smash product of two types x and y if they're pointed. And this is going to be a hit, which is generated by, first of all, points coming from x and y. I'm writing them in this angled bracket just to distinguish from a regular product. And then you have this additional base point and higher constructors, which basically will force x smash y to become a kind of a tensor product. This is not really important. I'm just saying it's a fancy product, and that's the way I'll treat it in this talk. All right, we will need suspensions. And again, well, you can define suspensions in many ways. So, okay, yeah, it's denoted by sigma x if you haven't seen that before. And you can, for example, define the suspension of the type x by saying that it's the smash product with a circle. But there are also more direct alternatives. We don't really need implementation details here. In this talk, all we need to know is that when x is pointed, there's this nice sort of pointed adjunction between between suspensions and loop spaces. So pointed maps out of a suspension, the suspension of x into y is the same thing as pointed maps out of x into the loop space of y. I'll be using this all the time in this talk. So yeah, remember it. So whenever I want to define a map f from suspension of x into y, I'm gonna just define it as a map from x into omega y instead, and I'll denote this associated f by just f tilde. All right. So one example of this is if you want to define the addition of two functions, f and g, coming from the suspension of x going into y, you define f plus g by defining it on the right-hand side again of this equivalence. And so you define f plus g tilde, which is a map from x into omega y, by just saying that f plus g tilde applied to x is just f tilde x path composed with g tilde x. So if you're interested, or if you didn't remember, this is what gives rise to the group structure on homotopy groups. But that's not that important for our purposes today. All right, here's another thing you can do with suspensions. So if you have two pointed types x and y, and you have a map f going from suspension of x into z, and a map g going from suspension of y into z, we can define the so-called generalized Whitehead product, which is denoted f bracket g, just like before. And this time, this guy is going to go from the suspension of the smash product of x and y into z. And how do we define this guy? Well, we again use this adjunction, and we work on the right-hand side. So we define fg tilde, going from x smash y into omega z instead. And we simply define it by sending the pair x and y to this kind of commutator word. So it goes to f tilde inverse, f tilde inverse g f g tilde inverse. Yeah. So very, very cute short construction, and this is it. This is the generalized Whitehead product. So just as a disclaimer here, because also I think Tom might use that version in his talk. Very often you don't use the suspension of the smash product here, you use the join of x and y instead. These two guys are equivalent. Using the suspension of the smash product makes it a bit more easy to iterate the Whitehead product. So it makes it easier to state the Jacobi identity, for example. But this is not super important. All right. So we have defined our generalized Whitehead product, which was of this type. To quickly mention that you get the usual Whitehead product on homotopy groups by just setting x to be the n sphere and y to be the m sphere. And then you use that spheres are suspensions, and you use that smash product of spheres are again spheres, and you will end up getting something that is of the right form. So it's a very straightforward generalization of what you want. So why not just forget about the specialized sort of homotopy version of Whitehead product homotopy group version of Whitehead products and just work with the generalized version all the time. Well, in order to do so, we will need to come up with the appropriate statements of bilinearity, symmetry, and Jacobi for the generalized Whitehead product. So let's do that. First of all, bilinearity, we don't have to make any changes. The statement for the specialized homotopy group version of Whitehead products and the version for the generalized Whitehead product will look exactly the same. So for example, left linearity will say that if you have f and g going from suspension of x into z, and you have some h going from suspension of y into z, left linearity just says that f plus g bracket h is f bracket h plus g bracket h. No changes to be made there. When stating symmetry, we need to be a bit more careful. So symmetry, we want to compare f bracket g with g bracket f, right? Up to a sign. But here the issue is that the domain of g bracket f is of this form, and the domain of f bracket g is of this form. So we need to make sure to apply this correction equivalence, which just swaps the smash product involved. So symmetry can be reduced now to this diagram, commuting. So that's the version of symmetry that we want to prove for the generalized Whitehead product. And the Jacobi identity is a bit annoying because it asks us to identify now 3 maps which all have different domains. So we want to sort of identify this guy, and this guy in a suitable way. But they all have these quite ugly nested domains. But fortunately, again, all of these domains are equivalent. So you just pull out suspensions to the front and you rearrange the smash products, and then you see that these guys are all equivalent to the double suspension of x smash y smash z. So you can state the Jacobi identity by requiring that the top map here, the top composition here, is equal to this composition plus this composition. Okay, so these are the appropriate generalizations of the properties. And what's nice now is that, for example, the Jacobi identity stated this way, we don't have any signs anymore. So all the signs are gone. So it's kind of nicer to work with the generalized version, anyways. Okay. So how do we prove these properties? Well, okay. So first of all, we never constructed the Whitehead product directly as a map like this, right? We always worked on the right-hand side of this suspension loop space adjunction. So what we really did was we constructed f bracket g tilde going from x smash y into omega z. So it would be nice if we could keep working on this side of the adjunction when we state the properties like symmetry and Jacobi. So let's try to translate also these properties now to the right-hand side of this adjunction. So what happens then? Well, what happens then is you get something actually that starts looking really cute. So let's fix f going from suspension x into w, g going from suspension y into w, and h going from suspension z into w. And as a technical assumption, I'm going to now also assume that x, y, and z are themselves suspensions. So for example, x will be the suspension of some other pointed type x prime. I'll justify this in a second. And then we fix 3 points, x, y, and z in x, y, z. And for ease of notation, I'm just going to write bold x for f the loop we obtain by applying f tilde to x. And I'm just going to write bold y for the loop obtained by applying g to y, and same thing for z. So this is just nice shorthand notation. And with this notation, the left linearity, for example, can be reduced to proving this equality. this is now an equality in the loop space of W. So it's just left linearity really boils down to proving that these two words of loops are equal. You get this just by unfolding definitions, really. And right linearity will be the same thing, of course, or similar thing. Symmetry will reduce to showing that these two words are equal. And the Jacobi identity is not as fun, but you can phrase it, or you can state it at least. I'm not gonna do this one in detail. Okay, so since some of these look horrible, let's just focus on symmetry. And now when we sort of get to this point, the proof is gonna start looking really, I mean, it's almost going to be anticlimactic because the proof becomes so simple. So what is the idea? How do you prove this thing? Well, the dream would be if we could just commute these two paths, then we would be done. But a priori, this is illegal. You can't just willy-nilly commute paths in an arbitrary loop space. However, with this additional suspension assumption we made, we will turn out to be allowed to commute some paths. So here's what we want to prove. I'm keeping it up here. If you look at the left-hand side here, we can view the left-hand side as consisting of two subwords. So the first word is just x inverse yx, and the second word is just y inverse. And I'm going to view these guys as functions in y. And by doing so, I can actually view them as pointed functions in y. So actually what these guys are pointed functions going from y into loop space of w. Now, since I made this additional assumption that y was itself a suspension, you can apply the suspension loop space adjunction again, and you actually get from Ekman-Hilton that these two guys must commute. So Ekman-Hilton gives us that the word 1, word 2 is the same thing as word 2, word 1. So we can rewrite the left-hand side, which was this, by just swapping the first three guys with the last guy. And then what we do is we play the exact same game again. Now we group these three guys together and this guy together. And we view these as words now indexed by x. And again, these will be pointed functions of this form. And again, x will be a suspension. So we are allowed to commute using Ekman-Hilton. And when you commute these guys, well, you're actually done. This is exactly the right-hand side of our identity. And, you know, it's almost stupid, the proof at this point, right? And that's kind of what I wanted to tell you about. It feels so anticlimactic. But that's because I also chose to do the easiest case, which was the symmetry property. If you do this for if you want to look at left linearity, or bilinearity, or the Jacobi identity, you do end up having to solve non-trivial word problems. Still something that you could do after your first algebra course, really. But you have to sit down and think about which paths to commute and in which order. So now I use this trick, I think, twice for the symmetry proof. I think if you want to do the Jacobi one, it's something like 11 times you have to swap things around. So it's not as trivial. But it's a really cute approach, I think. And so this additional suspension requirement was really what got me stuck when I was trying to prove this for a long time, because I didn't realize it was needed. Because when you look at the classical literature, it's kind of hard to isolate. But really what this corresponds to, this additional suspension requirement that made the proof work, is really the fact that Whitehead products are, or the usual Lie algebra properties of Whitehead products really are supposed to apply only in dimension greater than 1. So if you translate this back to the usual Whitehead products, it just says that the bilinearity, Jacobian, and symmetry applies in higher dimensions, which is the way it's supposed to be. So the main takeaways: Whitehead products are well behaved in hot, we can prove things about them. That's good. We can finally use them as they are supposed to be used. But also, I think it's nice to see that proofs that are quite complicated, often in the classical literature, can be so short and cute in hot, and that's really what I wanted to tell you about.
Hey, have any questions for Axel?
Hi, thanks for the very nice talk. So you mentioned again at the end this suspension assumption. Is it possible to give like a counterexample of where these generalized, like these nice properties don't hold if you don't have suspensions?
Yes, and that's what really made me doubt maths for a while. Before I accepted the suspension assumption, I came up with with some counterexamples, and I thought I had broken maths. So I think so. What you do is so it's really important not just that it's a suspension, but it's a suspension of a pointed type. So, for example, you can let it be a suspension, but you can just let it be the suspension of the empty type. And then you could, I think, using left linearity, if left linearity were to hold, I think you could prove that pi one of any type is abelian, which is in general. So, but I don't have the counterexample exactly in mind right now. But I know that linearity breaks things at least.
Okay, thanks. And then maybe somewhat related, if you assume to have all these nice properties for such type X and Y and Z, like let's say, is it then possible to relate X to some sort of suspension of a pointed type? Like, are you able to show that this is somehow as good as it gets?
Oh, that's a good question. It feels like I want to say yes, but on the other hand, I never have enough feeling for example, the Jacobi identity to to understand exactly what it says. That's a good question. I have to think about it. I'm not sure, but my spontaneous feeling would be kinda yes.
Okay, thanks.
Anybody else? I have a quick thing. So this proof you say is not the classical proof. And is this generalized Whitehead product something that's classically talked about, or is that also?
Ah, yeah. Thank you for. I should really say that. Yeah, it's classically talked about. It came. So it's Arco, which I think is like 20 years after the original definition of the Whitehead product, and he does prove these properties, these generalized properties, but it's hard to translate exactly into hot, and the proofs are quite sort of analytic in nature. But yeah, no, this is classically known. Everything I'm saying here.
Okay, thanks. All right, so I think that's it for this. We'll move on to the next. Let's thank Axel again.